Welcome to the first video on transformer assembly. So first let us go through the construction of a transformer, then we'll go to the profile views. See, whenever you are drawing the assembly drawing, it is nothing but going for orthographic projections of a machine. Orthographic projection in the sense you are going to go for two-dimensional representation of a three-dimensional object. All your real world objects are three-dimensional in nature. Same with the transformer or DC machine, maybe DC generator or AC generator, whatever it might be. All these machines appear to be 3D for your visualization. When you have to put it on paper, you'll have to go for orthographic projection. That is, you'll have to represent two-dimensional views. So whenever you have to represent two-dimensional views, you should understand first what are those profile views that are expected. So before going into those orthographic projections, first let us go through the main parts of a transformer that you'll have to represent. So first of all, here you are able to see the image of a transformer. Already you have studied about the transformers. The main parts of a transformer are the laminated core type construction. You'll be having LV winding, you'll be having HV winding, you'll be having high voltage bushings, and you'll be having low voltage bushings. To this low voltage bushings, low voltage winding will be connected, and HV winding will be connected to this high voltage bushings. And then here you are having LV coils and you are having HV coils, and transformer tank is there here. You people have visited Kavika also, so you'll be having a better picture of the transformer. Next, we'll talk about the various parts of a transformer. So here the first part is laminated core assembly. These are the laminations available. Laminations are nothing but it is not a solid part. Instead, many such laminations will be used. So many of you are maybe having a confusion with respect to laminations. So to make it clear regarding a lamination, I'll just give you a simple example. Just consider 1 pound of bread. If it is not sliced, it is nothing but a solid representation. If you slice the bread and join all those pieces to make 1 pound, it is nothing but laminated arrangement. Similarly, here also for the transformer core, we are having laminated arrangement. And the next part of the transformer is LV and HV windings, that is low voltage and high voltage windings. Next, coming to the types of transformers, based on the construction you are having two types, core type and shell type, and based on the lamination you are having cruciform core and multi-stepped core. So here in the core type you are having single phase and then three phase. Shell type also you are having single phase and three phase. So I hope you remember the difference between core type and shell type. In core type, windings surround the core, but in shell type, core will surround the winding. So this is this single phase core type transformer contains two limbs of the core over which the windings will be wound. In three phase, it contains three limbs. The core contains three limbs, and over the three limbs the winding will be wound. Now coming to the shell type arrangement, you can see on the middle limb the winding is wound, and this is for a three-phase shell type transformer where inside this particular limbs you are seeing in the middle limb or the innermost limb the winding is wound. This is R phase, this is Y phase, and this is B phase. And here you can have a look at the core. This is the core, and over the core you are having LV winding, you are having HV winding, and this is a two-stepped core. Similarly, you will be having multi-stepped core. So this is your core, and on the core you are having LV and HV windings. The most important thing that you should be aware before doing an assembly drawing is the orthographic views, especially the two-dimensional orthographic views, which are nothing but front view, top view, side view. If you have a 3D object, you should be able to visualize how it looks from the front, how it looks from the top, and how it looks from the side. So in order to make you to visualize that, I have taken an example of a cucumber here. You're able to see a cucumber. So this cucumber, this is the end view or side view of a cucumber, and this is the front view of a cucumber. If you place the cucumber in this manner, this is front view and this is side view. So first I have taken the end view here, end view of the cucumber. If you slice the cucumber in the end view, whatever you are able to see is called as sectional end view, because you are sectionalizing the end view. You are able to see sectional end view. You are cutting or you are slicing the end view. Whatever you are seeing is called as sectionalized end view. Suppose whenever you are cutting it, if you cut it only to one half of it, whatever you are able to see is called as half sectional end view. This is called as half sectional end view. Always remember, this is the end view or side view. If you slice the cucumber completely, it is sectional end view. If you slice it only to one half, it is half sectional end view. Similarly, you are having front view. I told you this is the front view. If you slice it in the front view, whatever you are able to see here is called as sectional elevation. If you slice it only to half of it and retain the second half, it is called as half sectional elevation. So the sectional views are very, very important. So for your reference, I'll repeat this once again. So I've taken a cucumber and this is the end view. If you slice it completely, it is called as sectional end view. If you slice it only one half of it, it is called as half sectional end view. Similarly, you are having front view or elevation, sectional elevation. If you slice it completely, it becomes sectional elevation. If you slice it only to the half, it becomes half sectional elevation. So coming to the transformer assembly, now we have understood the construction parts of a transformer and we have seen the profile views. Now we have understood what is elevation, what is sectional elevation, what is half sectional elevation. Similarly, plan, sectional plan, half sectional plan. Now whatever you have seen for an example, same thing has to be imagined for a machine called transformer. So coming to the design aspects, coming to the types of core, you are having square core, cruciform core or two-stepped core, and you are having three-stepped core. Already in machine design you would have studied about all these three types. So for our calculation purpose, I am just representing it once again. The width of the stamping here in square core is 0.71 D and the diameter of this core is D. And here coming to two-stepped core, the width of the largest stamping is 0.85 D and that of the second step is 0.53 D, where D is nothing but the diameter of the circumscribing circle. Similarly, coming to three-stepped core, the first stamping is 0.42 D, second stamping 0.7 D and the largest stamping 0.9 D. Now let us start with the first problem. Let me read the statement. Draw the sectional plan of one limb of a single phase 11 kV by 440 volts transformer with the following details. Cruciform core, diameter of the circle D is equal to 33 centimeters. Inside and outside diameters of LV and HV winding are 35, 39, 44, 49 centimeters respectively. The core laminations are fixed by two end plates of thickness 3 mm by M12 bolt. So now let us try to understand this line by line. What is expected in the problem is you are supposed to draw the sectional plan. See, in the previous slides I have told you what is sectional plan. Sectional plan means if you slice it, whatever you are able to see, that is what you are supposed to represent for a transformer. And he is asking you to do it for one limb. And remember, he is asking you sectional plan. That is, top view has to be drawn for one limb of a single phase 11 kV by 440 transformer. 11 kV by 440 means he is talking about distribution transformer with following details. The type of core is cruciform type. Cruciform means two-stepped. And the diameter of the circumcircle is given as 33 centimeters. Inside and outside diameters of LV and HV winding are given as 35, 39, 44, 49 respectively. And all these core laminations are fixed by two end plates having thickness 3 mm with a type of bolt called as M12 bolt. Now before drawing this assembly, you'll have to go for rough sketch. So the intention behind going for rough sketch is you should be able to visualize what you are trying to draw. So if you are able to visualize, then the drawing becomes simple. So first of all, you are dealing with single phase transformer. Single phase, that's why there are two limbs here. On two limbs you are able to place the windings, and out of which you are supposed to represent sectional plan of one limb. That is, you are supposed to draw only one limb, and here elevation is being shown, that is front view is shown. You are supposed to draw the top view of this. So here if you imagine from the top, if you see this from the top, this is how it looks like. And remember, I have shown you, I have drawn a blue line here, I have drawn a line here in between, that means it is cut. Just imagine this particular drawing is cut at this particular place. If it is cut, whatever you are seeing in the lower half part, you are supposed to draw, and that too for only one limb. Only one limb you should consider. And from the top, if this is cut, if it is sectionalized, this portion is to be shown now from the top, and this is how it looks like. You have to imagine, see, there is a core here. On the core you are having LV winding, you are having HV winding. So if you see it from the top, you will be seeing one circle, you will be seeing another circle, and in between you will be seeing some core, and that core is a two-stepped core in this particular problem. Then whatever transformer elevation I have shown here, this is the side view for that. So from the side, the laminations look like this. It is a two-stepped core, and all these laminations are put together, they are joined together using a bolt, and this is your M12 bolt. This M12 bolt is put from both the sides to keep all the laminations together. So this is the rough sketch. So ultimately in this problem you are supposed to draw this. See, imagination is very important here. So I repeat this once again. This is the front view of the transformer, elevation of the transformer, where you are having the core, two limbs are there. On both the limbs you are having LV and HV windings. You are supposed to draw the top view here, and the two, not complete top view, sectional view. That's why I am sectionalizing this here, I am cutting this here. You are supposed to imagine whatever you are seeing in the lower half from the top, that has to be drawn. So you will be seeing only two circles and the core in between. This is what is supposed to be drawn. So for that, first we'll have to go for calculations. Since it's a two-step core, the following dimensions you have to see. Width of the largest stamping is 0.85D. Second step is 0.53D. Diameter of the circumcircle is given as 33 centimeters. So 0.85D is 28 centimeters. 0.53D is 17.5 centimeters. So now let us go to the expected preparatory sketch. So if you have to go for preparatory sketch, first you will have to draw the core, then we'll represent the windings. So for drawing the core, for your understanding, I have given the steps here. First and foremost, you are supposed to draw a circle of diameter 33 centimeters as given in the problem. Then divide this circle into four parts by drawing these center lines. You are able to see this. This is one line. This is another line. You are cutting the transformer. You are cutting the circle into four parts. Then you should locate A, B, C and D. See, in the cruciform construction, you can see that the width of the second step is 0.53D and width of the largest stamping is 0.85D. And I have drawn a line in the center. So you have one half of this and you have one half of 0.85D. See, I have drawn a line in the center of the circle. So you are left out with half of 0.53D and you are left out with half of 0.85D. Just draw a line in the center. So here I am going to locate this A. I am offsetting this line, center line, by 0.53D by 2, whatever may be the value. So by that value, I'll draw one line here. I'm just trying to offset this center line by a value 0.53D by 2. That is, from this center, at a distance of 0.53D by 2, I am drawing a line. Wherever this line meets the circle, you locate point A and point C. Similarly, from the center, I'll measure a distance of 0.85D by 2 to get this point. Here I'll draw a line, and wherever it meets the circle, I get B and D. See, I repeat once again. First, draw a circle of diameter 33 centimeters. Then draw the center lines. Divide the circle into 4 parts. From this center, take a measurement of 0.53D by 2. You will be getting this point. Then draw a line parallel to the center line. Draw a line, this line, parallel to the center line. Wherever it meets the circle, you get point A and you get point C. Then from the same point, that is the center of the circle, locate a point which is at a distance of 0.85D by 2. That is this point. Now draw this particular line. If you draw this line, it will meet the circle at points B and D. Now I have A, B, C and D. Remember, these lines whatever have been shown here are construction lines. After the core drawing is completed, they have to be erased. So better use a pencil for that. Now after locating A, B, C and D, I'll join a line from this center line. From A, I'll draw a line here and draw a line vertically, and I already know the shape of a cruciform core, so I can join this in this manner. I'll join A, B, C, D in this manner to get one half of the cruciform core. Next, whatever is being drawn here, in the same way, I need the mirror image of this on the left hand side. That is, whatever you have done here in order to locate A, B, C, D, same thing you do on the left side to get E, F, G, H. Join EA, join CH to get the complete cruciform core. This finishes the drawing of the core. Next, let us represent the windings. See, now already core is being drawn. Let us see step by step what has to be done. First, you have to draw the concentric circles with given diameters. See, as given 35 centimeter, 39, 44, 49 centimeter respectively. Just take a compass, just draw circles of this particular diameter, 35, 39, 44, 49. So you'll be getting, see, this is the first circle that is already been drawn in the previous slide. Now this is, see, this particular circle was 33. Next I draw another circle for 35, then I draw for 39, then 44, then 49. So I've just drawn all the circles. This is the first step that I have done. Next step is hatch the LV winding which is between 35 and 39. See, this is your circle of 35 and this is the circle of 39. In between whatever is there is our LV winding that has to be hatched, because in the problem they have given inner dia of LV winding and outer dia of LV winding which are 35 and 39. So in between 35, 39, whatever you are seeing, that section is LV winding. Hatch them. Then you have to hatch the HV winding which is between 44 and 49, because 44 is the inner dia of the HV winding, 49 is the outer dia of the HV winding. So in between you will be having the winding, hatch them. That completes the second step. First step, we have just drawn the circles. Next, identified the location of LV winding, HV winding, hatch them. Next, represent wooden planks in the oil duct for support purpose. This part what you are seeing here, between LV and HV winding, whatever is there here you will be having insulation. In larger power transformers, basically, there will be an oil channel or oil duct. which acts as an insulator and also for cooling purpose. So in order to hold them firmly, you need wooden planks. Wooden planks will be placed at regular intervals in this section. So I have represented, say, 1, 2, 3, 4, 5, 6, 7, 8, 8 wooden planks. And regarding wooden planks, you just have a question, maybe how many wooden planks should I place? See, there is no particular specification that you have to go for 8 or 4. To give a firm support between LV and HV winding so that it will not shake, we have to give wooden planks. You can design 4 or 6 or 8 according to the practical design requirements. Lastly, we'll represent the section and then M12 bolt. See, you have drawn the sectional plan. So in order to represent that, you are going to hatch the core. These horizontal lines, whatever I've drawn inside the core, is nothing but hatching the core. See, whenever you represent them using horizontal lines, it is clear that you have drawn a sectional plan. If you have not hatched, it is nothing but a plan. To show the section, you'll have to hatch them. So this is being done. And the last part is M12 bolt. We are representing the M12 bolt here. One bolt from this side, another bolt from this side. To hold all these laminations together, you need bolt from both the sides. So I'll just repeat B, that is drawing LV windings, HV winding and representing insulation. First step after the core. See, I'll come back to the core. I think you already understood how to draw this core with the circumscribing circle. This circle was 33 centimeter diameter. In this, the first step that you have to do is draw the concentric circles with the diameter, say 35, 39, 44 and 49. Just draw the circles with so and so dimensions. Then the inner diameter of LV and outer diameter of LV are 35 and 39. Whatever ring comes in between, hatch it. Then whatever comes between 44 and 49 is your HV winding. Hatch them. Use cross hatch patterns here for LV and HV. This finishes the second step. Third step is in between the LV and HV, where there is an insulation, represent wooden planks. Last step is to represent the section of the core. Just draw horizontal lines in parallel. Then finally represent M12 bolt from either sides of the lamination. This finishes the first problem. So please go through this video and I need your feedback, and in case you are having any doubts, please call me. First use these steps and try to draw it. You may not be able to do it for exact dimensions, say 35, 33, 35, 39, 44 in your sheet. I think you can do it in AutoCAD, or if you want to do it in sheet, you can assume 3.3, 3.5, 3.9, 4.4 and 4.9 centimeter as per your convenience. Follow it stepwise, do it, and then come back to me if you are having any doubts. If you are comfortable with this, I'll continue with the next problem. So based on your feedback, based on your feedback only, I'm going to go to the next problem.